All right, today's lecture will be on weak acids and bases. Up until now, we have been focused mostly on strong acids and strong bases. Strong acids and strong bases ionize 100% in solution. Therefore, you do not establish an equilibrium in your reaction container. Now, with weak acids and weak bases, there is an equilibrium established between the reactants and the products, and we can use the law of mass action that we learned about in the equilibrium unit to calculate a K value. And the K value will have a specific letter designation. Ka will refer to weak acids, and Kb will refer to weak bases. Because we established an equilibrium, we are back to our ice problems that we have been doing for several months now. You will have an initial concentration of your weak acid, you will have a change in concentration of your weak acid, and eventually you will have an equilibrium concentration of your weak acid. You have a generic example up on the smartboard here where the weak acid HA establishes an equilibrium between the hydrogen ion and the A negative anion. We can write a Ka expression. Remember, the Ka expression is going to be the concentration of the products raised to their coefficients divided by the concentration of the reactants. The same thing exists for a weak base. We've given you a more specific example for the weak base. The NH3 is going to behave as our base in this example, and the water is going to behave as the acid. So we're going to see the hydrogen ion or the proton move in that direction to establish an ammonium ion as one of our products, NH4 positive, and the hydroxide ion as our other product. There. We go ahead and write the Kb expression. We have the concentration of NH4 positive times the concentration of OH negative over the concentration of NH3. Notice once again that the water is not included in the Kb expression. Water is in the liquid state and therefore does not have an impact on the law of mass action, our Kb expression. Let's go ahead and do a couple of practice problems. The first one we have listed down at the bottom here, calculate the concentration of all the species present and the pH of a 0.0500 molar HAF solution. So, first thing that you need to recognize is that you are dealing with a weak acid. There are two ways that you can do this. First, we've got the list of strong acids memorized at this point. HF is not one of them, therefore we can safely assume that it is a weak acid. The other clue that we have that we're dealing with a weak acid here is that you must be given a Ka value in the problem. We'll start off by writing the equation. HF will establish an equilibrium with the hydrogen ion and the fluoride ion. We can write a Ka expression for this. We'll have the concentration of the hydrogen ion times the concentration of the fluoride ion divided by the concentration of HF. We'll then set up an ice chart, concentration of HF, concentration of H positive, and concentration of F negative. And we will have I for initial concentration, C for change in concentration, and E for the equilibrium concentration. We're only given one value. We know that this concentration right here initially is 0.0500 molar. We can safely assume initially, if it's not listed in the problem, that both the hydrogen ion concentration and the fluoride ion concentration both start at 0. If their concentrations start at 0, their change has no choice but to be a positive change. So we know the product side of our equilibrium is going to increase in concentration, and therefore, because it's a closed container, the reactant side must decrease. We do not know what the change is at this point, so we're going to call it X. We have a 1-to-1-to-1 ratio throughout our problem, so we're going to have minus X and plus X plus X as our change row. Therefore, our equilibrium values are going to be 0.0500 minus X, X, and X. We'll take those three expressions there and plug them into our Ka expression. So we'll have X times X over 0.0500 minus X, and we'll set that equal to the Ka value, 7.2 times 10 to the minus 6th. Because Ka is such a small value, most of our material is going to stay on the reactant side. Very little of the molecular HF will break apart into the hydrogen and fluoride ions. Therefore, X is going to be a very small number. X is going to be such a small number that it is not going to make a statistical difference subtracting it from 0.0500 when we only have two significant figures to work with. Therefore, I can assume that X is much, much smaller than the 0.0500. This allows the minus X to drop out of the problem. So I now have X squared over 0.0500 equals 7.2 times 10 to the 6th. I'm going to move the 0.0500 to the other side and take the square root. And I get a final answer of 6.0 times 10 to the minus 4th equals X. I've made an assumption here, so I need to check my assumption. Recall from our equilibrium unit and our equilibrium unit, checking your assumption is taking the X value that you get divided by the original number that you make the assumption by, and multiplying that by 100. And we get 1.2% there. That number needs to be less than 5, so we are safe to make the assumption at this step. At this point, we will go back to our ICE table. Remember, we are trying to calculate the concentration of all the species. So we've got X and X, so both of those. The H positive at equilibrium will be 6.0 times 10 to the minus 4th molar. The fluoride at equilibrium will also be that value. Then we will subtract that number from the 0.0500, and we're going to get, for my HF at equilibrium, 0.049 molar. The last step that we need to do is the problem also asks us to calculate the pH. So now we're going to use the square that we learned in the earlier lecture. We're going to go one side of the square from the hydrogen ion concentration to the pH. pH is the negative log of the hydrogen ion concentration. So negative log of 6.0 times 10 to the minus 4th. And we get a pH reading of 3.22. Percent ionization is our next topic for today. We have just shown you a check your assumption in the previous KA problem that we did. Checking your assumption is also the percent ionization. In other words, we are determining what percentage of our molecular acid or base has been transferred to the product side into ions. It is the exact same calculation that you've done when you check your assumption. We're just now going to check your assumption by a different name. If we go back to the previous problem that we just completed, I wrote check your assumption down here. We will now be calling this also percent ionization, but it is the exact same calculation that we have already completed. Another example that we have. We'll now do a KB problem. We're going to work our way around the square, calculating OH, H positive, POH, and pH of a solution that is 1.0 molar NH3. NH3 will behave as a base, a hydrogen ion acceptor, when in a solution with water. We will form NH4 positive and OH negative. We're ready to go ahead and write an ice chart for this. We'll have concentration of NH3, concentration of NH4 positive, and a concentration of OH. Again, we're not including water because water is in the liquid state. Our initial concentration of NH3 is 1.0 molar. Our initial concentration of our product ions are both 0, which means they're going to increase by X, and the reactant concentration will decrease by X. We'll have 1.0 minus X, X, and X as our three equilibrium expressions. We're ready to write our KB expression, concentration of NH4 positive times the concentration of OH negative over the concentration of NH3. Plug in my equilibrium expressions into the KB expression and set it equal to our KB value given in the problem, 1.8 times 10 to the minus fifth. We have a very small KB value, which means that most of the material will stay on the reactant side. Few ions will be produced. Therefore, it is safe for us to make the assumption that X is going to be way smaller than 1.0. That allows the minus X to drop out of the problem and simplifies the algebra tremendously. We end up with X squared over 1.0 equals 1.8 times 10 to the minus fifth. We solve that by taking the square root of 1.8 times 10 to the minus fifth equals X. And we have a final X value of 4.2 times 10 to the minus third. We have to check our assumption since we made it. We now know that we're calling check assumption by a new name, percent ionization. So we have 4.2 times 10 to the minus third divided by the 1.0 times 100, and that's going to give me 0.42%, less than 5, and that is good. Because this is a KB problem, we recognize that we just solved for our OH concentration. This number, 4.2 times 10 to the minus third molar, is our OH concentration. We have one corner of the square that we like to use. So that's the first of 4 answers we have to give in this problem. At this point now, I'm going to work my way around the square. So POH is going to be the negative log of the OH concentration. That is 2.37. Then pH will be 14 minus POH. My pH value is 11.63. And then lastly, my hydrogen ion concentration, 10 to the negative pH. And that number is 2.4 times 10 to the minus 12th molar.